In this lecture, we will start discussing the data path that we use to implement a processor. In general, we're going to be specifically talk about the RISC-V processor. This will be a series of lectures where we'll slowly build for a full microprocessor, RISC-V microprocessor in the end of the series. We're going to take it slowly, and we're going to be building one building block at a time. But sometimes we're going to be making some simplifications that later on we'll clarify. This is a good didactic way to build what will be in the end a fairly complex design. So let's start very simple, and let's start with some very basic logic design. The information in an electronic system, in a processor in general, is encoded in binary, where the binary information can be talked as being encoded where there is a low voltage in a water, you have the value 0. When you have a high voltage in a water, we have the value 1. This is not necessarily the only way to do it. We can do the other way around, and actually many circuits do the other way around, where they encode a 1 with a low voltage and a 0 with a high voltage. It's just a question of design. As long as you're consistent, either way works fine. There is one wire per bit, so whenever we have, for example, a data path, a bus, for example, that has 32 bits, there are 32 wires that have to go around the chip to convey that information. We can have multiple bit data encoded on multi-wire buses. So, and then we're going to represent those graphically by having a line. Sometimes it's a thicker line, and sometimes we put a number in the line to indicate how many wires that line has. So let's start with the building block for a circuit. Let's just abstract this as a box right now. And this box has a number of input signals and a number of output signals. Each one of those input signals is a wire, so each one of them is a bit. And also the output is 1 bit per wire. And we say that this circuit is a combiner if what the circuit does is takes the inputs and produces the output. A combiner has no memory, so we call this a combinatorial circuit, which means that any time that any of the input values change, the output values will change. And you can think of this change as being an immediate change. In reality, it's not, because there is a delay in propagating the signal through the different logic gates that I have in my combiner to go from the input to the output. We already talk about this delay when we talk about the adder, and this will happen here too. But the fact is that there is no holding back a change in the input. It will eventually affect the output after a certain amount of delay. And if I take my combiner and so here's my combiner, sorry. And I add a state to my combiner, and sorry that the video is cutting some of the lines, but this is a box that contains my combiner. Now I add the state to my combiner so that my combiner can change that state, and my combiner can also read the state. So the combiner will have signals that will be sent to the state storage so that the state can be updated. And also going to be able to read the value, the current state. And now the output will be produced by a combination of the current inputs and the current state. In this case, I have what's known as a sequential circuit, because this circuit can go into a sequence of states. It can go from one state to another. We also know this as a finite state machine construction. So that's the difference between the combinatorial and the sequential circuits. The combinatorial has no memory, and if there is a change to the input, it will propagate to the output. The sequential circuit, there is memory, there is a state, and the value of the output will depend on both the input and the state. So there are several elements in the design of a circuit that are known as combinatorial elements. So one example is the AND gate. So if I have two wires that come an A wire and a B wire, and I provide those as input to the AND gate, the output will be the AND function of the two inputs. That's a combinatorial circuit. Another example of a combinatorial circuit is the multiplexer. The multiplex has a switch, and the switch will tell which one of the two inputs, in this example of a two-input multiplexer, will go to the output. So by changing the value of the switch, I can make the I0 or the I1 input go to the output, and the other one does not pass. So one good analogy to make for a multiplexer is to think about a train set, a kid's train set, where I have the switch that can switch the direction that a train goes or that a train comes from. I have another type of combiner is my adder. My half adder that I had and even my full adder is a combiner, and my entire arithmetic and logic unit that does all the arithmetic and logic operation has no memory. It will the output in that unit will change after a certain amount of delay because of the delay that happens in the logic gates, but the output will change when the input changes, and it doesn't depend on any state. So the entire logic and so in the top I have the adder, but the entire logic and arithmetic unit, we refer to it as ALU, also is a combinatorial circuit. Sequential elements, the registers in my processor are all sequential elements. They have memory. They store information in between different clock cycles. So the typical element for a sequential element for a register, this is a single bit register presented in the slide here, would be the simplest one will have a data input, and we'll have an output that is the state. The letter Q is used because it's talk about the quiescent state, the state that I can be stable at. And typically in such an element, there is one input, that's the clock input. So if I have time here and I have the clock here, as we have seen already in our performance unit, the clock is a regular signal that keeps changing between low and high at very regular intervals. The time between two consecutive transitions from low to high is called the clock period. So what we have is that I can have a circuit, so this is the clock period, and I can have an input D. And in this type of diagram, I represent a signal as either being high or low for D, which means that it has a stable amount, but I don't know what that amount is. It could be 1, could be 0, but it is stable. And then I have these times where the input may make a transition. So if I make a transition of the input, and the same thing is true for my quiescent state. My quiescent state will be stable. And then when the clock period, when the clock transition happens, so the clock transition will make after a certain amount of delay, the output of my register here, my 1-bit register, will change. So this diagram is indicating that when the clock the clock signal makes a transition, the output of my 1-bit register will follow whatever was in the data input. And so the same thing keeps happening in every clock transition. The output copies the data input in this circuit, which we call synchronous flip-flop, or a clocked flip-flop. Flip-flop is the name that's used for the circuits that restore data. So of course, for our processor, this register here, this design, Let me just finish this animation. So I use the clock signal to determine when I update the stored variable. This is called an edge trigger device because the update happens when the clock changes from 0 to 1. But of course, the circuit is storing data in between the clock transitions, but it's following the data input at every clock cycle. This design wouldn't be very useful in my processor because it would cause all my registers to change in every clock cycle depending on the input that they have. And of course, I wanted to have some control about which one of my registers will change when a clock signal comes. And that control is given to me by another control input to my circuit that is my write input. So my write input is a control input now. And now what happens is that only when my write signal is true, that the output of my register will follow the input. When my write signal is false, when it's low, the output does not follow the input. The output remains the same regardless of what happens in the input. So now I have memory that can last for much longer. When I want to change what this memory is storing, I have a control signal that I can say, this is time to write now. And that's how I control writing into registers. When I execute an instruction, for example, I do an add T0, T1, T2, I want only the value of T0 to change when that instruction is executed, and I don't want any of the other registers to change. So I only will update on the edge, the clock edge, when the write control input is 1. So now that we understand how we store state and we understand how combinatorial circuits work, we can talk about clocking methodology. So what happens is that we have a state element somewhere in our machine, and we have some combinatorial logic that will take the value of that state, and through some combination, perhaps there will be some other inputs, will produce a new value for a different state or for a different state element. And because we have that the outputs of these state elements can only change at the clock transitions, I have this style of this methodology of signal clocking signal here, where the value of the state in each of those elements only changes when the clock makes a transition. And more commonly what I have is that this state element 1 and the state element 2 are the same state element, which means that I take the value of the state element, I do some logic combination with it. This state could be several bits. We have the example with a single bit, but I could have multiple of those forming a state, and then I could do a combination of those states to produce the new state. That's how I, for example, produce a counter. So the combinatorial logic will transform the data during the clock cycle and at the end or between the clock edges. And the input from the state elements will be also the output to the state elements, as the figure on the right is indicating. So now we can think about what is limiting the clock period. Why cannot we make the frequency higher and the clock period is smaller? What limits the amount of time that the minimum amount of time that I have to have for a clock period is the delay through this combinatorial logic. I cannot have a clock period that will be shorter than the longest delay in all my combinatorial logic. So this is an introduction to circuit design, and I will stop the recording now, and I will have a second part to this lecture where we'll be connecting these concepts with the instructions in a processor.